One already. Okay, human physiology depends on water. Water is a fascinating molecule, and biologists and astrophysicists alike will tell you that water is critical to how life exists on Earth. Anyway, okay. Now, the question I want you to answer for yourself is why. You've been told that your whole lives. So let's talk a little bit about why that's true. One is solubility. Because water is a polar molecule, it can hold other polar substances in solution, right? So that's your ions in particular. It would be a very short course in physiology if we had no ions to talk about, right? So solubility makes that happen. And I've got a picture that will show that a little bit in a minute. Reactivity. This is one people don't think often about. Is we think of water as passive in biologic reactions. It's not. Water is also a participant. Remember, some of the, what are we made of? Hydrogen, carbon, oxygen, and nitrogen. Well, hydrogen and oxygen are water. So that means we have this body of hydrogen and oxygen that we can put in and take out in our system. Right? So, for example, in our the mitochondria create some water. They add oxygen radicals and hydrogen ions together, releasing energy and creating water. So that's an example. Another way we react water in our systems is hydrolysis, right? Where we'll take a molecule AB, we'll split a water, and we'll make it AH and B H2, or I think that's probably supposed to be HO. My apologies. And then a dehydration, where we take two molecules and put them together, and we get a water out. Remember, these are all waters being made or destroyed in these processes. That's why we can call it reactivity. It's one of the reactants. Okay, so the polar nature of water allows for what we call hydration spheres to exist. Okay, so if we take sodium chloride crystal salt from the Himalayan mountains, right, and we put it in water and we mix it up, what's happening? Well, the chloride ions have a negative charge, but the water molecules have a positive side on the hydrogen side. So all the positives of the hydrogen sort of hang out next to the negative of the chloride. Same with sodium, but reversed. Sodium has a positive charge, so the oxygen end of the molecules sort of are pointed towards it all the time. This property allows us to dissolve a lot of polar materials in water. We're gonna talk about blood another day, but there are many grams of material dissolved in every deciliter of blood. So this property is very important. Now, in addition to ions, there are a number of other polar molecules which also benefit from this process. Glucose among them, right? Because glucose is a carbohydrate that's also polar, and this property means we can put a lot of glucose in water. We can dissolve a lot of it, which is useful because glucose is one of our primary energy molecules. Well, what about the flip side? What about a non-polar molecule? Well, non-polar molecules typically have long chains of carbon and hydrogen and very little oxygen. Remember, oxygen from chemistry, oxygen's kind of greedy. It likes to steal charge, right? So it tends to make things polar. In molecules that don't have a lot of oxygen, they end up non-polar. And therefore, they sort of don't mix with the rest. It's the classic oil on top of water. No matter how much you mix it up, you can't get it to dissolve. And it's because the molecular and ionic state is not right. However, proteins, yes, these guys, most proteins are polar. They have a negative end and a positive end, simplistically, or more accurately, they have negative regions and positive regions, right? So one of the reasons that protein is such an important part of our system is because it too has this polar characteristic. All right. Okay, some other important properties of water that make it critical. High heat capacity. Um, we have all put a pan on the stove and filled it with water and thought, oh my gosh, that's taking forever to boil. Why is that? Well, it's because water has a very high specific heat. In other words, it takes a lot of energy to change the temperature of water. How does that help us? It helps us stabilize our temperature, right? Because we're essentially big bags of water walking around, okay? As the temperature changes, we're hard to cool and hard to warm up. So it tends to stabilize our temperature in the environment. It also means that we have to spend less energy to maintain our temperature because water does that pretty well all by itself. Now, the flip side of that, which works in places that are not swamp-like, like Omaha right now, is that water, when it evaporates, it takes away a fair bit of heat with it. We tend to make excess heat. Humans tend to make excess heat. So the way we get rid of that heat is in part because of evaporative cooling, which totally breaks down when it's 100% humidity and 100 degrees outside, right? So if you're wondering if you're from somewhere where it's dry and you're like, well, this doesn't feel like 100 degrees, this feels like 190 degrees. It's all the humidity, right? You can't actually get any of your sweat systems to work right. All right, so high heat capacity and evaporation. Finally, vapor pressure is quite low. In other words, water is kind of difficult to make evaporate, which means we have an easier time holding on to our water. Okay, we all lose water through our skin, but compared to the amount of water we have in our surface area, we don't lose a lot that way. And the bit that we do lose helps us to stay cool. Okay, and then lubrication. That having negative ends and positive ends on the water molecules, when you take them under pressure and you slam them together, they get really slippery. Okay, because they repel each other. That makes water a very good lubricant. You put a small amount of water between two surfaces, and you dramatically reduce the friction that it takes to move those surfaces across each other. So we benefit from that too. Now, in addition to water, our lipids are also very good lubricants as well. You're going to make very good friends with a lot of lipid in the anatomy lab, okay? And one of the properties that you're going to find is very slippery, okay? Particularly when you have gloves on. All right. So what we find in nature tends to be electrolytes, as we call them. Minerals, they're also called inorganics, okay, because many of these are not carbon backbone molecules. When we put them in water, they dissociate into their ions. Hopefully, after all the chemistry that you've endured in your life, none of these ions are unfamiliar, right? Any of these unfamiliar? Okay, good. We're going to talk most about sodium, potassium. Calcium is my favorite ion. I'll tell you why later. Magnesium we'll talk not very much about. Phosphate we'll talk a tiny bit about. Sulfate a tiny bit about. Okay, we're going to spend more time than you want to spend in the next couple weeks talking about these two, sodium and potassium, because we have to build up to action potential in order to make the heart beat, right? I sort of look at my classes, how do we make a human being, or at least how do we figure out how it works? So today is sort of building blocks for that adventure.